In combinatorial mathematics, a cycle index is a polynomial in several variables which is structured in such a way that information about how a group of permutations acts on a set can be simply read off from the coefficients and exponents. This compact way of storing information in an algebraic form is frequently used in combinatorial enumeration. Each permutation pi of a finite set of objects partitions that set into cycles. The cycle index monomial of pi is a monomial in variables a1, a2. That describes the type of this partition. The cycle type of pi. The exponent of I is the number of cycles of pi of size I. The cycle index polynomial of a permutation group is the average of the cycle index monomials of its elements. The phrase cycle indicator is also sometimes used in place of cycle index. Knowing the cycle index polynomial of a permutation group, one can enumerate equivalence classes due to the group's action. This is the main ingredient in the Polya enumeration theorem. Performing formal algebraic and differential operations on these polynomials and then interpreting the results combinatorially lies at the core of species theory. Permutation groups and group actions. Let X be a set. A bijective map from X onto itself is called a permutation, and the set of all permutations of X forms a group under the composition of mappings, called the symmetric group of X. Sim. X. Every subgroup of sim. X is called a permutation group of degree X. Let G be an abstract group with a group homomorphism phi from G into sim. X. The image phi G is a permutation group. The group homomorphism can be thought of as a means for permitting the group G to act on the set X, using the permutations associated with the elements of G. Such a group homomorphism is formally called a group action, and the image of the homomorphism is a permutation representation of G. A given group can have many different permutation representations, corresponding to different actions. Suppose that group G acts on set X. That is, a group action exists. In combinatorial applications, the interest is in the set X. For instance, counting things in X and knowing what structures might be left invariant by G. Little is lost by working with permutation groups in such a setting. So in these applications, when a group is considered, it is a permutation representation of the group which will be worked with, and thus, a group action must be specified. Algebraists, on the other hand, are more interested in the groups themselves and would be more concerned with the kernels of the group actions, which measure how much is lost in passing from the group to its permutation representation. Disjoint cycle representation of permutations. Finite permutations are most often represented as group actions on the set X equals 12. N. A permutation in this setting can be represented by a two-line notation. Thus, 1, 2, 3, 4, 5, 2, 3, 4, 5, 1. Display style left. Begin matrix 1 and 2 and 3 and 4 and 5, 2 and 3 and 4 and 5 and 1, end matrix right. Closing curly bracket corresponds to a bijection on X equals 1, 2, 3, 4, 5, which sends 1, 2, 2, 3, 3, 4, 4, 5 and 5, 1. This can be read off from the columns of the notation. When the top row is understood to be the elements of X in an appropriate order, only the second row need be written in this one-line notation. Our example would be 2, 3, 4, 5, 1. This example is known as a cyclic permutation because it cycles the numbers around and a third. Notation for it would be 1, 2, 3, 4, 5. This cycle notation is to be read as Each element is sent to the element on its right, but the last element is sent to the first one. It cycles to the beginning. With cycle notation, it does not matter where a cycle starts. So, 1 2 3 4 5, and 3 4 5 1 2, and 5 1 2 3 4, all represent the same permutation. The length of a cycle is the number of elements in the cycle. Not all permutations are cyclic permutations, but every permutation can be written as a product of disjoint, having no common element, cycles in essentially one way. As a permutation may have fixed points, elements that are unchanged by the permutation. These will be represented by cycles of length 1. For example, 1, 2, 3, 4, 5, 6, 2, 1, 3, 5, 6, 4, equals 12, 3, 456. Display style left. Begin matrix 1 and 2 and 3 and 4 and 5 and 6, 2 and 1 and 3 and 5 and 6 and 4, end matrix right, equals 12, 3, 456. Closing curly bracket. This permutation is the product of three cycles, one of length 2, one of length 3 and a fixed point. The elements in these cycles are disjoint subsets of X and form a partition of X. The cycle structure of a permutation can be coded as an algebraic monomial in several dummy variables in the following way. A variable is needed for each distinct cycle length of the cycles that appear in the cycle. Decomposition of the permutation. In the previous example there were three different cycle lengths, so we will use three variables, A1, A2 and A3. In general, use the variable A to correspond to length k cycles. The variable I will be raised to the g power, where g is the number of cycles of length I in the cycle decomposition of permutation g. We can then associate the cycle index monomial k equals 1 n a k j k g. Display style prod underscore k equals 1 caret n a underscore k caret j underscore k g. Closing curly bracket, closing curly bracket. To the permutation g, the cycle index monomial of our example would be a1, a2, a3, while the cycle index monomial of the permutation 1, 2, 3, 4, 5, 6, 7, 8, 9, 1, 0, 1, 1, 1, 2, 1, 3, 14, 15, would be a13, a22, a42. Definition. The cycle index of a permutation group G is the average of the cycle index monomials of all the permutations G in G. More formally, let G be a permutation group of order m and degree n. Every permutation G in G has a unique decomposition into disjoint cycles. Say C1, C2, C3. Let the length of a cycle C be denoted by C. Now let Jk, G, be the number of cycles of G of length k, where 0, j, k, g, n, slash, k, and k, equals 1, n, k, j, k, g, equals n. Display style 0, leq j underscore k, g. LEQ, L floor N, K, R floor, M box, and sum underscore, K equals 1, caret, N, K, J underscore, K, G, backslash, equals N, closing curly bracket. We associate to G the monomial, C, G, A, pipe, C, pipe, equals, K, equals, 1, N, A, K, J, K, G, display style prod underscore C in G A underscore C equals prod underscore K equals 1 caret N A underscore K caret J underscore K G closing curly bracket in the variables A1, A2, and then the cycle index Z G of G is given by Z G equals 1 pipe G G K equals 1 N A K J K G display style Z G equals frac 1 G sum underscore G in G prod underscore K equals 1 caret N A underscore K caret J underscore K G closing curly bracket. Example. Consider the group G of rotational symmetries of a square in the Euclidean plane. Such symmetries are completely determined by the images of just the corners of the square. By labeling these corners 1, 2, 3 and 4, consecutively going clockwise, we can represent the elements of G as permutations of the set X equals 1234. The permutation representation of G consists of the four permutations 1 4 3 2, 1 3, 2 4, 1 2 3 4, and E equals 1, 2, 3, 4, which represent the counterclockwise rotations by 90 degrees, 180 degrees, 270 degrees and 360 degrees respectively. Notice that the identity permutation E is the only permutation with fixed points in this representation of G. As an abstract group, G is known as the cyclic group C4, and this permutation representation of it is its regular representation. The cycle index monomials are A4, A22, A4, and A14 respectively. Thus, the cycle index of this permutation group is Z C 4 equals 1, 4, A 1, 4, plus A 2, 2, plus 2, A 4. Display style Z C underscore 4 equals frac 1, 4 left. A underscore 1 caret 4 plus A underscore 2 caret 2 plus 2 A underscore 4 right. Closing curly bracket. The group C4 also acts on the unordered pairs of elements of X in a natural way. Any permutation G would send X, Y, XG, YG, where XG is the image of the element X under the permutation G. The set X is now A, B, C, D, E, F, where A equals 12, B equals 23, C equals 34, D equals 14, E equals 13, and F equals 24. These elements can be thought of as the sides and diagonals of the square or, in a completely different setting, as the edges of the complete graph K4. Acting on this new set, the four group elements are now represented by ADCB, EF, AC, BD, E, F, ABCD, EF, and E equals A, B, C, D, E, F, and the cycle index of this action is Z, C, 4, equals 1, 4, A, 1, 6, plus A, 1, 2, A, 2, 2, plus 2, A, 2, A, 4. Display style Z, C underscore 4, equals frac 1, 4 left. A underscore 1, caret 6 plus A underscore 1, caret 2, A underscore 2, caret 2 plus 2 A underscore 2, A underscore 4 right. Closing curly bracket. The group C4 can also act on the ordered pairs of elements of X in the same natural way. Any permutation G would send X, Y, xg, yg. In this case we would also have ordered pairs of the form x, x. The elements of X could be thought of as the arcs of the complete digraph D4, with loops at each vertex. The cycle index in this case would be Z, C, 4, equals 1, 4, A, 1, 16, plus A, 2, 8, plus 2, A, 4, 4. Display style Z, C underscore 4, equals frac 1, 4, left. A underscore 1, caret 16 plus A underscore 2, caret 8 plus 2 A underscore 4, caret 4, right. Closing curly bracket. Types of actions. As the above example shows, the cycle index depends on the group action and not on the abstract group. Since there are many permutation representations of an abstract group, it is useful to have some terminology to distinguish them. When an abstract group is defined in terms of permutations, it is a permutation group and the group action is the identity homomorphism. This is referred to as the natural action. The symmetric group S3 in its natural action has the elements S3 equals opening curly bracket, E, 23, 12, 123, 132, 13, closing curly bracket, display style S underscore 3 equals E, 23, 12, 123, 132, 13, backslash closing curly bracket, and so, its cycle index is Z, S, 3, equals 1, 6, A, 1, 3, plus 3, A, 1, A, 2, plus 2, A, 3, display style Z, S underscore 3, equals frac 1, 6 left. A underscore 1, caret 3, plus 3A underscore 1, A underscore 2, plus 2A underscore 3, right. Closing curly bracket. A permutation group G on the set X is transitive if for every pair of elements X and Y in X there is at least one G in G such that Y equals XG. A transitive permutation group is regular, or sometimes referred to as sharply transitive, if the only permutation in the group that has fixed points is the identity permutation. A finite transitive permutation group G on the set X is regular if and only if G equals X. Cayley's theorem states that every abstract group has a regular permutation representation given by the group acting on itself as a set by right multiplication. This is called the regular representation of the group. The cyclic group C6 in its regular representation contains the 6 permutations. One line form of the permutation is given first. Well, 34, 5, 6 equals 1, 2, 3, 4, 5, 6, 2, 3, 4, 5, 6, 1 equals well, 34, 5, 6, 3, 4, 5, 6, 1, 2 equals 1, 3, 5, 2, 4, 6, 4, 5, 6, 1, 2, 3 equals 1, 4, 2, 5, 3, 6, 5, 6, 1, 2, 3, 4 equals 1, 5, 3, 2, 6, 4, 6, 1, 2, 3, 4, 5 equals 1, 6, 5, 4, 3, 2. Thus its cycle index is Z, C, 6 equals 1, 6, A, 1, 6, plus A, 2, 3, plus 2, A, 3, 2, plus 2, A, 6, display style Z, C underscore 6, equals frac 1, 6 left. A underscore 1, caret 6 plus A underscore 2, caret 3 plus 2A underscore 3, caret 2 plus 2A underscore 6 right. closing curly bracket. Often, when an author does not wish to use the group action terminology, the permutation group involved is given a name which implies what the action is. The following three examples illustrate this point. The cycle index of the edge permutation group of the complete graph on three vertices. We will identify the complete graph K3 with an equilateral triangle in the Euclidean plane. This permits us to use geometric language to describe the permutations involved as symmetries of the equilateral triangle. Every permutation in the group S3 of vertex permutations, S3 in its natural action, given above, induces an edge permutation. These are the permutations. The identity: no vertices are permuted, and no edges. The contribution is A 1 3. Display style A underscore 1 caret 3. Closing curly bracket. 3 reflections in an axis passing through a vertex and the midpoint of the opposite edge. These fix one edge, the one not incident on the vertex, and exchange the remaining two. The contribution is 3 A 1 A 2. Display style 3A underscore 1 A underscore 2. Closing curly bracket. 2 rotations, one clockwise, the other counterclockwise. These create a cycle of 3 edges. The contribution is 2 A 3. Display style 2A underscore 3. Closing curly bracket. The cycle index of the group G of edge permutations induced by vertex permutations from S3 is Z G equals 1 6 A 1 3 plus 3 A 1 A 2 plus 2 A 3. Display style Z G equals frac 1 6 left A underscore 1 caret 3 plus 3 A underscore 1 A underscore 2 plus 2 A underscore 3 right. Closing curly bracket. It happens that the complete graph K3 is isomorphic to its own line graph vertex-edge dual, and hence the edge permutation group induced by the vertex permutation group is the same as the vertex permutation group, namely S3, and the cycle index is Z S3. This is not the case for complete graphs on more than 3 vertices, since these have strictly more edges. N2. Display style binom N2. Then vertices N. The cycle index of the edge permutation group of the complete graph on 4 vertices. This is entirely analogous to the 3-vertex case. These are the vertex permutations, S4 in its natural action, and the edge permutations, S4 acting on unordered pairs, that they induce. The identity: this permutation maps all vertices, and hence, edges, to themselves, and the contribution is A 1 6. Display style A underscore 1 caret 6. Closing curly bracket. 6 permutations that exchange 2 vertices. These permutations preserve the edge that connects the 2 vertices as well as the edge that connects the 2 vertices not exchanged. The remaining edges form 2 cycles, and the contribution is 6 A 1 2 A 2 2. Display style 6 A underscore 1 caret 2 A underscore 2 caret 2. Closing curly bracket. 8 permutations that fix one vertex and produce a 3 cycle for the 3 vertices not fixed. These permutations create 2 3 cycles of edges, one containing those not incident on the vertex, and another one containing those incident on the vertex. The contribution is 8 A 3 2. Display style 8 A underscore 3 caret 2. Closing curly bracket. 3 permutations that exchange 2 vertex pairs at the same time. These permutations preserve the 2 edges that connect the 2 pairs. The remaining edges form two cycles and the contribution is 3a 1 2 a 2 2. Display style 3a underscore 1 caret 2 a underscore 2 caret 2. Closing curly bracket. 6 permutations that cycled the vertices in a 4 cycle. These permutations create a 4 cycle of edges, those that lie on the cycle, and exchange the remaining 2 edges. The contribution is 6a 2a 4. Display style 6a underscore 2 a underscore 4. Closing curly bracket. We may visualize the types of permutations geometrically as symmetries of a regular tetrahedron. This yields the following description of the permutation types. The identity. Reflection in the plane that contains one edge and the midpoint of the edge opposing it. Rotation by 120 degrees about the axis passing through a vertex and the midpoint of the opposite face. Rotation by 180 degrees about the axis connecting the midpoints of 2 opposite edges. 6 rotaniflections by 90 degrees. The cycle index of the edge permutation group G of K4 is ZG equals 1, 24, A, 1, 6, plus 9, A, 1, 2, A, 2, 2, plus 8, A, 3, 2, plus 6, A, 2, A, 4. Display style Z, G, equals frac 1, 24, left. A underscore 1, caret 6 plus 9 A underscore 1, caret 2, A underscore 2, caret 2, plus 8 A underscore 3, caret 2, plus 6 A underscore 2, A underscore 4, right. Closing curly bracket. The cycle index of the face permutations of a cube. Consider an ordinary cube in 3 space and its group of symmetries. Automorphisms. Call it C. It permutes the 6 faces of the cube. We could also consider edge permutations of vertex permutations. There are 24 automorphisms. The identity. There is one such permutation and its contribution is A, 1, 6. Display style A underscore 1, caret 6. Closing curly bracket. 6 90-degree face rotations. We rotate about the axis passing through the centers of the face and the face opposing it. This will fix the face and the face opposing it and create a 4 cycle of the faces parallel to the axis of rotation. The contribution is 6, A, 1, 2, A, 4. Display style 6A underscore 1, caret 2, A underscore 4. Closing curly bracket. 3 180-degree face rotations. We rotate about the same axis as in the previous case. But now there is no 4 cycle of the faces parallel to the axis, but rather 2 cycles. The contribution is 3, A, 1, 2, A, 2, 2. Display style 3A underscore 1, caret 2, A underscore 2, caret 2. Closing curly bracket. 8 120-degree vertex rotations. This time we rotate about the axis passing through 2 opposite vertices, the endpoints of a main diagonal. This creates 3 cycles of faces. The faces incident on the same vertex form a cycle. The contribution is 8, A, 3, 2. Display style 8A underscore 3, caret 2. Closing curly bracket. 6 180-degree edge rotations. These edge rotations rotate about the axis that passes through the midpoints of opposite edges not incident on the same face and parallel to each other and exchanges the 2 faces that are incident on the first edge, the 2 faces incident on the second edge, and the 2 faces that share 2 vertices but no edge with the 2 edges, i.e., There are 3 2 cycles and the contribution is 6. A. 2. 3. Display style 6A underscore 2, caret 3. Closing curly bracket. The conclusion is that the cycle index of the group C is Z. C equals 1. 24. A. 1. 6. Plus 6. A. 1. 2. A. 4. Plus 3. A. 1. 2. A. 2. 2. Plus 8. A. 3. 2. Plus 6. A. 2. 3. Display style Z. C equals frac 1, 24, left. A underscore 1, caret 6 plus 6 A underscore 1, caret 2, A underscore 4 plus 3 A underscore 1, caret 2, A underscore 2, caret 2 plus 8 A underscore 3, caret 2 plus 6 A underscore 2, caret 3, right. Closing curly bracket. Cycle indices of some permutation groups. Identity group N. This group contains one permutation that fixes every element. This must be a natural action. Z. E. N. equals A. 1. N. Display style Z. E underscore N. equals A underscore 1, caret N. Closing curly bracket. Cyclic group Cn. A cyclic group Cn is the group of rotations of a regular n-gon. That is, n elements equally spaced around a circle. This group has phi d elements of order d for each divisor d of n, where phi d is the Euler phi function, giving the number of natural numbers less than d which are relatively prime to d. In the regular representation of Cn, a permutation of order d has n d cycles of length d. Thus, Z. C. N. equals 1. N. D. Pipe. N. Phi. D. A. D. N. Slash. D. Display style Z. C underscore N. equals frac 1. N. Sum underscore D. N. var phi. D. A underscore D. caret N. D. Closing curly bracket. Dihedral group Dn. The dihedral group is like the cyclic group, but also includes reflections in its natural action. Z. D. N. equals 1. 2. Z. C. N. plus, opening curly bracket, 1. 2. A. 1. A. 2. N. minus 1. slash 2. N. odd 1. 4. A. 1. 2. A. 2. N. minus 2. slash 2. plus A. 2. N. slash 2. N. even. Display style Z. D underscore N. equals frac 1. 2. Z. C underscore N. plus begin cases frac 1. 2. A underscore 1. A underscore 2. caret N 1. 2. An N M box odd. Frac 1. 4. left. A underscore 1. caret 2. A underscore 2. caret N 2. 2 plus A underscore 2 caret N 2 right. An N M box even. End cases. The alternating group An. The cycle index of the alternating group in its natural action as a permutation group is Z. A. N. equals J. 1 plus 2. J. 2 plus 3. J. 3 plus N. J. N. equals N. 1 plus minus 1. J. 2 plus J. 4 plus K equals 1. N. K. J. K. J. K. K equals 1. N. A. K. J. K. display style z, a underscore n equals sum underscore j underscore 1 plus 2j underscore 2 plus 3j underscore 3 plus c dots plus nj underscore n equals n frac 1 plus minus 1 caret j underscore 2 plus j underscore 4 plus c dots prod underscore k equals 1 caret n k caret j underscore k j underscore k prod underscore k equals 1 caret n y underscore k caret j underscore k. Closing curly bracket. The numerator is 2 for the even permutations and 0 for the odd permutations. The 2 is needed because 1 pipe a n pipe equals 2 n display style frac 1 y underscore n equals frac 2 n. Closing curly bracket, closing curly bracket, closing curly bracket. The symmetric group Sn. The cycle index of the symmetric group Sn in its natural action is given by the formula Z S n equals J1 plus 2 J2 plus 3 J3 plus n Jn equals n1 k equals 1 n k j k j k k equals 1 n a k j k. Display style z s underscore n equals sum underscore j underscore 1 plus 2j underscore 2 plus 3j underscore 3 plus c dots plus nj underscore n equals n frac 1 prod underscore k equals 1 caret n k caret j underscore k j underscore k. Prod underscore k equals 1 caret n y underscore k caret j underscore k. That can be also stated in terms of complete Bell polynomials. Z S n equals b n 0 a 1 1 a 2 n minus 1 a n n. Display style z S underscore n equals frac b underscore n 0 backslash a underscore 1 1 backslash a underscore 2 dots n1 backslash a underscore n n. Closing curly bracket, closing curly bracket, closing curly bracket. This formula is obtained by counting how many times a given permutation shape can occur. There are 3 steps. First, partition the set of n labels into subsets, where there are j, k, display style j underscore k, subsets of size k. Every such subset generates k slash k, display style k, k, cycles of length k, but we do not distinguish between cycles of the same size, i.e., they are permuted by s, j, k, display style s underscore j underscore k. This yields n k equals 1 n k j k k equals 1 n k k j k k equals 1 n 1 j k equals n k equals 1 n k j k j k. Display style frac n prod underscore k equals 1 caret n k caret j underscore k prod underscore k equals 1 caret n left frac k k right caret j underscore k prod underscore k equals 1 caret n frac 1 j underscore k equals frac n prod underscore k equals 1 caret n k caret j underscore k j underscore k. closing curly bracket, closing curly bracket, closing curly bracket. There is a useful recursive formula for the cycle index of the symmetric group. Set Z S 0 equals 1. Display style Z S underscore 0 equals 1. And consider the size L of the cycle that contains N, where 1 L N display style begin matrix 1 LEQL LEQN end matrix. There are N minus 1 L minus 1 display style begin matrix N1 choose L1 end matrix. Ways to choose the remaining L minus 1 display style L1 elements of the cycle, and every such choice generates L display style begin matrix frac L end matrix different cycles. This yields the recurrence Z S N equals 1 N G S N K equals 1 N A K J K G equals 1 N L equals 1 N N minus 1 L minus 1 L L A L N minus L Z S N minus L display style Z S underscore N equals frac 1 N sum underscore G in S underscore N prod underscore K equals 1 caret N Y underscore K caret J underscore K G equals frac 1 N sum underscore L equals 1 caret N N1 choose L1 frac L L A underscore L NL backslash Z S underscore NL closing curly bracket, or Z S N equals 1 N L equals 1 N A L Z S N minus L display style Z S underscore N equals frac 1 N sum underscore L equals 1 caret N Y underscore L Z S underscore NL closing curly bracket. Applications. Throughout this section we will modify the notation for cycle indices slightly by explicitly including the names of the variables. Thus, for the permutation group G we will now write Z G equals Z G A 1 A 2 A N display style Z G equals Z G A underscore 1 A underscore 2 L dots A underscore N closing curly bracket. Let G be a group acting on the set X. G also induces an action on the K subsets of X and on the K tuples of distinct in elements of X. See hashtag example for the case K equals 2. For 1Kn, let Fk and Fk denote the number of orbits of G in these actions respectively. By convention we set F0 equals 1. We have a. The ordinary generating function for Fk is given by K equals 0 N F K T K equals Z G 1 plus T 1 plus T 2 1 plus T N display style sum underscore K equals 0 caret N F underscore K T caret K equals Z G 1 plus T 1 plus T caret 2 L dots 1 plus T caret N closing curly bracket and B. The exponential generating function for Fk is given by K equals 0 N F K T K slash K equals Z G 1 plus T 1 1 1 display style sum underscore k equals 0 caret n f underscore k t caret k k equals z g 1 plus t 11 l dots 1 closing curly bracket. Let G be a group acting on the set X and H a function from X to Y. For any G in G, H, Xg is also a function from X to Y. Thus, G induces an action on the set Yx of all functions from X to Y. The number of orbits of this action is Z, G, B, 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 where B equals Y. This result follows from the orbit counting lemma, also known as the not-Burnside's lemma, but traditionally called Burnside's lemma, and the weighted version of the result is Polya's enumeration theorem. The cycle index is a polynomial in several variables, and the above results show that certain evaluations of this polynomial give combinatorially significant results. As polynomials, they may also be formally added, subtracted, differentiated and integrated. The area of symbolic combinatorics provides combinatorial interpretations of the results of these formal operations. The question of what the cycle structure of a random permutation looks like is an important question in the analysis of algorithms. An overview of the most important results may be found at Random Permutation Statistics. Notes. Brualdi, Richard A. 2010. 14. Poly Accounting. Introductory Combinatorics. 5th ed. Upper Saddle River. N.J. Prentice Hall. pp. 541-575. ISBN 978-0-13-602040-0. Cameron, Peter J. 1994. 15. Enumeration under group action. Combinatorics. Topics. Techniques. Algorithms. Cambridge. Cambridge University Press. pp. 245-256. ISBN 0-521-45761-0. Dixon, John D. Mortimer, Brian. 1996. Permutation Groups. New York. Springer. ISBN 0-387-94599-7. Roberts, Fred S. Tesman, Barry. 2009. 8.5 The Cycle Index. Applied Combinatorics. 2nd ed. Boca Raton. CRC Press. pp. 472-479. ISBN 978-1-4200-9982-9. Tucker, Alan. 1995. 9.3 The Cycle Index. Applied Combinatorics. 3rd ed. New York. Wiley. pp. 365-371. ISBN 0-471-59504-7. Van Lint, J. H. Wilson, R. M. 1992. 35. Poly: A Theory of Counting. A Course in Combinatorics. Cambridge. Cambridge University Press. pp. 461-474. ISBN 0-521-422-60-4. Marco Riedel. Polya's enumeration theorem and the symbolic method. Harold Fripperting. 1997. Cycle indices of linear, affine and projective groups. Linear algebra and its applications. 263. 133-156. DOI. 10.1016 S0024-3795. 96. 00530-7.